Hey, Nick, can you hear me?
I can hear you.
Oh, perfect. It's Dan.
Yeah.
It's Dan from Axiom.
Yeah, we're live right now.
Okay.
We're just waiting.
Yep.
So I will put my audio again.
I'm going to just mute myself. Okay.
Go ahead. Christian, can you hear me?
Yes, I can hear you.
Okay, so we are going to wait a little bit more to see if anyone else wants to join.
Yes.
I suggest maybe we start at 05.
How many registration do you have?
I think it was around 20 people.
Okay.
But sometimes, people join late. So
Okay.
we'll start at 05 in 2 minutes.
Okay. Yeah. You can present and I will mute my audio.
Okay. All right. I'll start in 2 minutes.
Okay. Thanks.
All right, it is 12:05 Boston time, and we're going to start. So thanks for joining this webinar, everyone. Today, we will be talking about laser beam quality, M² measurement, and we will be focusing on the CinSquare tool by Synergy. So I am Nick. the host here, and I am also with Philip from Axiom Optics, and we also have someone from Synergy here with us, Christian, all the way from Germany.
Hello.
So the webinar outline for today, this is about an hour total. The first 15 minutes, we'll be presenting Axiom Optics and Synergy. We'll do an overview of the CinSquare system, and we will talk after that about the ISO norms and how they apply to the CinSquare tool. After that, we'll talk about the system accuracy. We will have a look at the software. And after that, we'll go to a live demo. So we have here Philip, who is in our lab in Boston, and we have a live setup going on. He's saying hi. We have a laser going through a fiber, and we'll be doing some live measurements with the system. Going back to this, we'll finish off by reviewing some what we call exotic measurements of beams with, for example, astigmatism or different modes. And we'll finish with a 15-minute Q&A. So if you pay attention to your Zoho right now on the left, you should see a section called Q&A with a question mark. Feel free to type in questions in there as we go. Philip will be looking through them and answering some of them on the fly. And if we can't answer some of them, we will answer them at the end during the Q&A. All right, so Axiom Optics is our company. It's based we have several offices. The company was launched in 2010, and we're a North American distributor for optical instrumentation, and more specifically, advanced imaging systems and optical metrology systems. If you go on our website, axiomoptics.com, you will see our products line. We have first, from left to right, advanced light microscopy, which are essentially add-ons for microscopes. We have camera and vision systems, laser beam characterization, which is what we'll be focusing on today. We have some optical metrology for wavefront sensing and the light field camera, for example. We have adaptive optic solutions, including deformable mirrors to use with a wavefront sensor. And we also offer some positioning, high accuracy exapods. So our company, we're 6 of us, and we offer sales support and technical expertise on all our products. We have our headquarters / lab in Boston, and we also have offices throughout California. You can see below a list of some of our customers. We work with different industries, labs, universities, and government agencies. So Synergy Technologies is a German-based company, and they are our partner for all the solutions for laser beam profiling. They offer an array of products, going from simple beam profiling to profiling a laser line. You can also have tools here at the bottom left for focused beams to look at the focus spot. And today we will be focusing on the beam quality measurements for collimated beams mainly, in order to characterize their M² and other parameters. So if we have a look at the CinSquare system overview, first we need to have a quick review of what needs to be done to calculate the M² and to be ISO standard. So the norm says that you need to be focusing your laser beam with aberration-free lens, and after that you need to use a regression equations to fit the hyperbola to the data points. So basically we are focusing the beam and we will be traveling the camera along the focus to acquire different images at different positions and extract the information. Once we have a mathematical fit, we can extract with known formula the values for divergence, the waist diameter, the Rayleigh length, the M², and so on. So what you see here is a top view from the system. You have your laser coming from the right here. We have two mirrors outside of the system for alignment. They can actually be removed in an industrial setup where you could go straight in the system. We have a filter wheel with OD filters and a clear aperture if you want to attenuate your laser beam power, followed by a lens wheel. This wheel will focus your beam, and after that you have a linear stage with a beam profiler attached that will be going through the different position and through the focus. Note that the reference plane, so the measurements, for example, the waist position, is in reference to this position here, which is the aperture / entrance of the system. So this system is called a straight beam configuration, where after focusing, the beam stays straight. There is also another configuration that we call folded beam, where everything is the same except we add two mirrors to fold the beam, and the beam profiler is typically at the end here. This allows us to have basically a greater effective travel range when we need longer distances, and that makes a more compact system. So the CinSquare, there's many flavors of lasers, so therefore there are many different configurations. We have different travel range configurations, all the way to 600 effective if we use a 300mm model with a folded beam. All of the lenses that we use are plano-convex, uncoated, made of BK7 or quartz with a quality of λ/10 typically, and each lens has a focal length calibration. The optic size, we can work with 1-inch optics, but if you have a large beam, typically that's exceeding 75% of 1 inch, we can go to 2-inch optics, which will then allow you to do the beam caustic on the very large beams. In terms of spectral range, we cover pretty much from UV to the SWIR wavelength, depending on the different lenses we use, the beam profiler, and the attenuations. We can cover pretty much the whole spectrum from 190 nanometer all the way to 1800. In terms of laser power, we have typically a low power system with a maximum of 50 milliwatt, and for high power, we can add a prism attenuator. If I go back here one, instead of the mirror that you have here, we can replace that with an attenuation unit to dump some energy and use higher power. About the ISO norm, so all the measurements delivered by the system are ISO compatible with ISO standards. There are two norms, 1 and 2, and the software and the system support both of them. The ISO 11146-1 is for stigmatic and simple astigmatic beams. But more importantly, we support the norm 2-2, which is for general astigmatic beam. And this feature is a unique feature to the CinSquare tool, and that's not supported by any competitor as far as we know. All the measurements, it's automatic, and we compute ISO standard measurements when possible. If for some reason your beam is non-conform, we will tell you why and give you some results, but we will let you know that it's not ISO conform. Here is an example, and we will actually open one at the end of a beam with a strong astigmatism. And you can see that we have a cutting plane here, and we have on the right the two orientations from that plane. The results depend highly on the cutting plane, and the software allows you to actually rotate this cutting plane here and use any orientation. You can do that during or after the measurement. We can also adjust the axis, the main axis, where the astigmatism is maximum. In the case of beam with very strong astigmatism, what happens is that we take the whole envelope of the beam in order to do the mathematical fit and calculate the parameters. So you can see here, we're not seeing different cut sections, but we see really the whole envelope. In terms of accuracy, which is something that's important if you are in an industrial environment and you need to stay within specs, the way we achieve high accuracy is by having measurements with a well-known reference laser. So typically, Synergy uses helium-neon at 543 with all the lenses on the CinSquare. So that's the reference. In terms of acceptance criteria, each system that comes out of the factory, we know for sure that the M² that is given will be between -2 and +3% of the known value. In terms of the D0, which is your beam waist diameter, the accuracy is ±4%. And about the Z0, which is the absolute waist position, same thing, ±4%. So having those, acceptance criteria guarantee high compatibility between different devices. If you have several systems, you want to make sure they're all giving the same results, and that's very important when we use those in an industrial environment. Typically, people that make lasers and they characterize the lasers after production and before they get out of the factory. So here we're going to go through 3 slides in a row that basically show you the measurement accuracy. Here, this is for the M2, M² parameter, and you can see all those dots here are different CinSquare systems, and they all stay within the specs and the criteria. If I have a look at the D0, you can see -4 +4%. Same thing again, each dot that you see is a different system. So that's to show you that we always stay within the specs. And lastly, about the accuracy in time, this is less than 1% over time. So highly repeatable and stable measurements. In terms of software, the software from Synergy is called RayCi. We use the Pro version. There is also compatibility with XML RPC interfacing, which allows you to have remote control. We also have SDK with a wrapper for C, C++, C#, LabVIEW, and we also support Python. So that's important for people that want to do their own coding. We have a detailed documentation and code examples, and Christian, actually, who's with us today, is the main actor when it comes to RayCi, and he can answer any question about the software since he's doing the software. For industrial environments where we want people maybe to take measurements without being overwhelmed by all the features of the software, we have a tool that is a simplified interface that we call CinSquare Control Tool, and that allows for easy data acquisition with simple steps. So it's a step-by-step process that people can follow in order to acquire easily data from the system. But today we will be showing the RayCi software, which is the complete interface. So before we do the live demo, I'm just going to show you quickly this file. So this is a file that typically Synergy has, or that myself have, where we know the setup that we're using. So the CinSquare model, the camera that's inside, the lens that we're using. And then, for example, a customer approach us, we ask for the laser parameters. Once we have those parameters here, we can basically simulate what we will have in the CinSquare system, and we can see if we stay within a certain regions in terms of focus spots, so that at the end of the day we're able to give you ISO standard measurements. So no matter what the laser you have, if you have different lasers, we can simulate, and if it doesn't fall within a standard system, we can then do a custom system for your specific laser. So keep in mind that we can also do customization. Right now, we will go to the lab where we have our CinSquare set up. So if you see at the bottom here, Philip will show you we have a little laser, a red laser at 632 with 30 milliwatt output. Going straight, you can see here the laser spot. The laser goes through a fiber and to a collimator over there on the right. The beam comes out highly collimated, so very low divergence. Goes straight to the first mirror, second mirror, and it enters the system over here. So when we give results for the waist position and things like that, that's our reference plane right here. After that, we have the two wheels. The first wheel is for OD filters, typically 1, 2, 3, 4, 5, and we have a clear aperture as well. Followed by the focusing wheel with different lenses in the wheel, and also a clear aperture if you don't want to focus your beam and look straight at the beam. So that's the overall setup. We already aligned it so that we get the laser spot on the camera. So I will switch to the RayCi Software interface right here. I already opened a few windows, but basically you can see here your live beam in the software. Right now, this is a live view of your beam. That is not focused. So we're doing standard beam profiling right now, and we're showing you the raw beam without any lens focusing it. We can see here in the live window, we can do some measurements of width. So these are the different methods available. Typical methods used, are the second moments, which is used for the beam caustic, beam quality measurements, actually. And you can see here again the norm. We can do a Gaussian fit. So if we do that, you can see here with a cross section, basically the Gaussian fit, and then our live signal on top of it. You can do two different methods at the same time if you want to compare the results. So for example, here we have a Gaussian fit and second moment, and the results are given here in the result table here. Before we go to the beam quality, these are actually all the different measurements you can do with the RayCi software. So single measurements, I won't go through that. This is simply taking a measurement of the beam we have right now. Time series allows you to take measurements in time. Let's say you want to take measurements for an hour or several hours every 10 minutes. You can set up the layout of your measurement, and you can acquire many images over time and get a report at the end. We can also do, I think this is important, beam stability or pointing stability. So pointing stability is basically looking at the stability of your centroid in the XY position over time. And you can see here we have the centroid X and Y, and we give you a different representation of the data here, which is basically spatially the probability of where your laser is over time. So this can go on forever, basically, because we're running it right now, but you can also set, an interval of time in between data points. So right now we're going to go to the beam quality measurement. So once you click this, typically, no, let me close this one here. No, let me close this one. No. Typically, if you start the beam quality, I already entered earlier the wavelength, but basically you will be asked for the wavelength that you're using. So this should be mentioned. So for the N² measurement, we basically have 4 windows that we work with. In the top left, we'll see our beam. So I think right now the easiest would be to just start. We have a 400 millimeter lens right now, so Philip can actually adjust to the lens, and we can see here, we're going to see our beam being focused. All right, so you can see the beam here. We adjusted the exposure time to avoid saturation. This is all automatic. Right now we're selecting the lens. Note that there is an option to have an automatic wheel and to have the software switch lenses. If that's required, we can do it. Right now, all I need to do is activate the AOI adjustment. So you can see when I do this, basically the software tracks the beam location, and this region of interest here is where the actual measurement is taken. We already did a background calibration, which is basically turning off your laser, taking images in the dark or without the laser on for background subtraction. In this window here, we select the lens. Before we start, there are several different modes that can be used. So full automatic means that you click start and the system will do the measurements on its own. You have nothing to do. There is a scanning mode where basically the translation stage will not stop and will scan quickly through the beam. That is much faster, but that will not give you specifically an ISO standard measurement. And there is also an alignment mode, which is a back and forth of the stage to help you align your beam. And there's a live mode, which maybe we can show at the end, which is basically going to the M² where the beam waist is located, and looking at the data over there in real time, and you can adjust your beam and it will redo the calculation on its own. So let's do a full automatic measurement. Right here, you can see on the x-axis, that's the position of the stage. Right now, the stage is right here. I can take the stage and move it to the left if I want, or I could also input a value over here. So right now I move the stage and you can see the beam on the left that it's changing. So all I need to do for the measurement is just click start. And right now we're taking measurements. Maybe you can hear, so there's really nothing to see here because everything's happening inside. But you can see the beam being constructed. And you can see here on the top right, the beam caustic, you have 2 different colors. That's for your 2 orientations. Right now we are in beam coordinate. So that's why we're not lab coordinate, which would be, perpendicular to your monitor, basically. And right now the software is taking data. It will go wherever it needs to go. mainly in the first and third relay length to get the data points. The ISO standard says that you need 5 points of measurements in the first and third relay length on each side of the waist, so almost 20 measurements. So right now the measurement is complete. You have here a representation, 3D representation of your beam. Over here we have the different measurements. We can go through each point. You can see the spot right here for each position. On this axis here, we said it was the location of the stage. So you can see those straight lines here show you the waist position for both axes. And then the dotted line will be the start of the relay length. So all the values are displayed right here. Caustic Q, caustic V. So right now, it's telling us there's probably some simple astigmatism going on. So that's probably because we don't have, the focus is not the same on both axes over here. And you can see the different parameters. So you have your caustic position, which is the position of your waist. Here, this is actually taken, sorry, I have to click here. This is taken in the raw beam. So that's Z0. The beam waist diameter is D0. So here we have a waist of about 3 millimeter. That's for the raw beam. So that's, before focusing. So it is not the measurement that we see when we focus the beam. So if we want to look at the focus spot after the lens, which is, looking right now, we would see a beam diameter of 178 microns, so 180 microns. So that's after the lens, after focusing. But typically, if you're doing this, you want to know your waist size before for the raw beam, which here is 3.3. Divergence, 0.5 milliradian. The beam quality parameter, the M², and the propagation factor K. So you have this for each axis. That's the norm 1 here. Here we're able to change the coordinates, which is unique to the RayCi software. So we can go, for example, to laboratory, and you can see now that you have something maybe more common, which is an X and Y configuration. So if you look at that now, the planes are in the orientation of the lab. If you take the norm 2, we said earlier, this is for highly astigmatic beams, but just to look at it right now, if we do the ISO norm -2, you can see basically that we have the whole envelope of the beam that is taken, and we do the fit on the whole beam and not by sections. So that's why we have only one curve. And on that one curve, we can calculate the values as we described. So basically, once you have done this measurement, you can save the measurement, create a report very quickly. Let's see, I'm gonna try it even though I didn't test it. There's a button says here report. This is supposed to generate a report very easily right here. You can put your own logo. You can set up here all the different parameters of your laser, and then you will have a summary of all the results. So very useful for quick report instantaneous report. And everything can be entered over here when it comes to your laser parameters and everything. If you want to redo a measurement, you simply clear the measurement and you take another one. It's very simple. Maybe what we can do now is to do a scan. So a scan will be a quick measurement, basically without stopping. So that should take less than 30 seconds. So let me see, hit start. The stage is moving to one extremity and it's already starting to take data. So here you see we're not stopping. We're taking measurements on the fly. They're more or less equally spaced out. So you see we're not really trying to go more or less in the different Rayleigh length. We're just taking with the same increment of distance each time. All right, measurement is finished, basically getting the same results. So right now, I think it would be a good time for Christian to jump in, and maybe what we can do is open a few measurements to show another kind of beam. So I'm gonna close this right here. And we already opened a few measurements. So Christian, if you want to jump in, and we can start maybe not with this one, maybe a good start would be to do the highly astigmatic one.
Yeah.
This one.
Yeah, this is an example with a high astigmatic beam. And you can see here we have a small tilt of between the orientation of the beam to the coordinate system of the camera. But for example, if we switch to the coordinate system, to the camera, to the X and Y direction, can you do this?
Well, sorry. Oh, the rotation?
Yeah, the orientation.
Okay, over here. So we take an astigmatic beam here, and we can rotate.
Yeah, laboratory coordinate system.
No, laboratory 0, but if I want to move it, it's free. Astigmatism takes you to the actual orientation that is found. But free here, we can basically change the cutting plane.
Right. And what you can see here is the results will strongly depend on the orientation of a coordinate system and also the fit results. You can see if you don't have a good alignment for the beam in the coordinate system, the point doesn't really lie on this curve, on the fitting curve. So this is a good example to see how it or why it's important to align your coordinate system to the beam.
Do you want me to switch to the next one?
Yeah, we can switch to the next one.
Okay. So this one is, I think, a donut-shaped helium neon.
Yes, with a donut-shaped helium neon laser with a misaligned resonator. And yeah, we have another example also with a different, from the same laser, but it shows a different laser mode.
This one.
Yeah, this one. So here you can also see it's important. The beam coordinate system is roughly rotated by 45 degrees to the laboratory coordinate system.
I think that's the last one we had.
Yeah, these are some not Gaussian examples. Yeah.
Yeah, non-Gaussian. So maybe we can start the Q&A if anyone has any question and wants to jump in.
Okay. I have questions. I don't see any questions there, but I think there's just maybe some typical questions. If you can hear me, right?
Yes.
Yes. So this is Philippe. So in your for your setup, how does it? Here obviously the laser is continuous. Can you describe a little bit what happens if you use a pulse laser? For example,
yes. So
10 hertz.
If we go, can't really see here, but at the back of the system you have your connections. You can use a hardware trigger TTL signal with a BNC kind of cable, coaxial cable in the back, and that will be used to trigger the camera for low repetition rates. Now, if you have a laser that is 10 kilohertz, unless you're taking a sampling of your pulses, one every 100 or one every 10 or 100, you will be considered continuous, obviously. But a way could be to maybe synchronize one in every 100 or 1,000 pulses.
Okay. Another question, and here actually there's a question from Thomas, and it's also another question I was going to ask you. Thomas is asking if the beam stability measurement functions are available on other Synergy profiling units, for example, those that would be used in additive manufacturing machines. So
yes, so for the focus beam profiler, the FBP, we are running RayCi Pro with it. It comes with it by default. So you would find the same functions. And actually, if you look earlier, I was showing you this, well, in the beam quality, we were changing between the after lens or the raw beam. For the FBP, we're on the focus beam already, so we're measuring the beam quality of that focus beam. And you can do, just like here, you can do a beam stability, which monitors not only the centroid, but also other parameters. So if we hit that, you'll see that we measure centroid X and Y, and also peak power. And we also measure the width, minor, major axis, and the if you have a twist, if your beam has an angle, we can measure that as well. So you can monitor several parameters, which basically will give you an idea of what thermal lensing is doing in your process. And you'll see that if you run this and turn on your laser in your powder bed fusion machine, you'll see that you'll see the power coming up, but you also see a little jitter, and also on the width, you'll see that you need to wait a little bit to be stable. So that this is available with the focus beam profiler. The difference between pointing stability and beam stability: pointing stability is only looking at the centroid X and Y, and the other one, beam stability, is, like I was showing, monitoring several parameters at the same time, including the centroid.
And so another question is, how long would you recommend waiting for the beam to stabilize in a LPBF setup that you just mentioned?
Well, when we do measurements, I've seen two kinds of of operation. Like sometimes the laser is continuously firing, but sometimes it's on and off, on and off. So if it's on and off for a while, there will be a certain equilibrium at some point. But if you start from a cold system and everything is cold and you're starting your laser, you haven't used the machine yet, you will have some thermal lensing. And what that will affect is not necessarily centroid and all those things. What it mainly affects is the position of your waist on the z-axis, because it's going to act as a focusing element. So I don't really know how long. That's basically why you would purchase an FBP, is to figure this out.
Okay. One question I have, maybe to understand this a little bit more, because we just showed an M² measurement on a beam that's
Yes.
about, what, 10 milliwatts, 20 milliwatts.
Yeah.
What Thomas' questions are about is for much higher power, I suspect. And so how do you
Yes.
translate this to a much higher laser power? Let's say 100 watts or maybe a kilowatt.
How do I translate what the kind of results?
Yeah, how do you use this method, or can you use this method for 100 watts or a kilowatt laser?
Yes. So if you give me maybe, let's see, I do have a measurement, and maybe I can send it to Thomas, but I do have a measurement of a measurement taken on a SLM machine, SLM 125 at 400 watt. And I could share that with you. It gives you an example, but basically the output will be the same. You will know your focus spot, and you will know the waist position, and your reference will be your building plate. So if you have a 0 on your building plate and you think that's where your focus is, well, the software will let you know, and it will let you know just right here. It will tell you the caustic position in reference to your 0 on the building plate, if maybe you're 200 microns above or below. So here, everything applies to the focus beam profiler and higher power, except that instead of working on the raw beam, you will be working in the after lens here. So it means that you're not looking, you're looking at the focused beam.
Mm-hmm. Okay. I don't see other questions here, but I guess this also applies to what wavelengths could this apply to? Here we're at 630.
So,
Yeah.
so for the high power or low power, basically for the high power, it's mainly the 1070, but there's actually other options. One thing we didn't mention is on some of them, we can calibrate the power at one wavelength. That applies to the FBP. So if you work at 1070, we could additionally provide a power measurement with about 5-6% accuracy. So it's not as accurate as a power meter, but that could be added. Otherwise, for the CinSquare, 50 milliwatt is kind of like the upper limit without using a prism attenuator. Otherwise, you can maybe go to 50 watt continuous with the addition of a prism attenuator. And for the FBP, there's two models, 400 or 1 kilowatt CW or pulse.
And now the FBP is a different architecture, Nick, right? There's no, I mean, it's already, the beam is already focused, right? So you don't have to have the lens and things like that.
Yeah, the building plate is acting as our stage up and down, and basically the focus beam profiler acts as an attenuation unit and the camera to take the data on the attenuated beam.
Okay. Okay, good. I don't see other questions here. So
No, if maybe I think there's a poll that we didn't discuss, but if you before you guys leave, if you want to answer, it's in the poll section, I believe, on the left, and you can quickly. There's like 3 questions I think that people can answer.
I'll start the poll. So
Okay.
this is gonna take 30 seconds. We have 3 questions, and I'm starting the first one now.
All right. So that should be on your screen, and you can answer. All right, Nisha, can you maybe move on to the second?
Okay. Starting the second poll. And
maybe go to the third. Yes.
yeah, and we're starting a third one.
Okay, so this is gonna finish off soon. I'd like to thank everyone that took the time to join in, and thank you also to Christian who helped us setting this up and for his time, and thank you Philip who is in the lab. So thank you everyone, and if you want more information, we'll follow up, or you can follow up with us. And I believe this was a recorded webinar, and you will be able to find it later on our YouTube page or through our website. I'm not sure, Neshe, if you can tell more about that, but it'll be available.
Yeah, we will follow up with you once the webinar recording is available, and it will be posted on our YouTube channel and also on the CinSquare product page in about a week.
All right, thank you, Neshe. Thank you, everyone, and everyone have a good rest of your day. Bye-bye.
Bye, Nick. Thanks for your nice presentation.
bye-bye.
Bye-bye.